Okay, aqueous electrolysis. In the electrolysis of a molten salt, all we do is we take sodium ion, so like in a down cell, and this is liquid, plus electrons produce liquid sodium metal, and chlorine, two chlorides go to chlorine gas and 2 electrons. So that's all we have to choose from in molten salt are the 2 ions. But when we react, we do electrolysis in aqueous solution, say we just sodium chloride here, we also have these 2 things that can happen, but also these 2 reactions. Reduction of water forms hydrogen and OH minus, or the oxidation of water can produce oxygen and H plus and electrons. So these are the other options for each electrode now. So we have to decide which one is going to happen. Of these, so this is going to take place at this is going to be the reduction. Will this one take place or this one? This is the oxidation. Will this take place or will this one? So that's what we're going to study. On its own, though, water on its own will form into hydrogen and O2. And let me get this right. So that'd be 2, 2. Yeah. So on its own, that's what water would like to do, but it has a high resistance to doing this on its own. So that's why we do these aqueous solutions. Even if we're just trying to form hydrogen and oxygen, doing it without the ions in the solution to reduce that resistance doesn't work very well. So here's first solution is the electrolysis of sulfuric acid. Sulfuric acid dissociates 100% into H plus and SO4 minus. It doesn't go all the way to just where we get 2H plus and sulfate ion. It just forms these 2, 100%. At the cathode, the possible reduction half reactions are hydrogen reducing, H plus reducing to hydrogen gas, or water reducing to hydrogen gas and OH minus, but then since we're in an acidic solution, that OH minus would react to form water, which is going to produce the same thing. And we're going to have water here produced. It's going to produce 2 waters again, which kind of negates the whole thing. But if at the very least we can see all that's going to be produced would be hydrogen on its own. So hydrogen gas. So at the cathode, nothing happens but the production of hydrogen, or the reduction of H plus. At the anode, though, we have 2 possible reactions. We have the one for water, because water is in there, and then we have the sulfate that can form S2O8 2 minus. And we look at the voltages here, and I think I kind of already covered this on the next page, so let's go there. So, like I said, the 2 reduction half reactions produce H plus, or H2 from H plus. So this is the only thing that happens at the cathode. At the anode, we have here these 2 reactions, and you can see that this one has a lower negative voltage than this. Now remember, a negative means that neither of these want to occur. But if we're going to put a voltage across, and that's what we're doing in electrolysis, I should have said this earlier, but we force the reaction to go by putting a voltage across it, making it forcing it to be spontaneous. Neither of these is spontaneous, but notice this one is closer to being spontaneous than this one. So if we put in a voltage of, say, 0.2, neither of these is going to go. If we put in a voltage of 0.4, neither of them is going to go, but if we get up to a voltage of plus 1.4, then this one will begin to happen, whereas this one won't. If we go to 1.6, this one does, this one doesn't, 1.8, 1.9. We have to get up to plus 2.01 volts to get this one to occur. Now, but this one is still going to be predominant. So when we consider this reaction, since they have such a difference in voltages, this is the only one that occurs. We would have to put a huge amount of voltage, it's called an overvoltage, to get this thing to happen. So this one is the only one that occurs. So overall, let's see if I got, yeah. So let's look at the characteristics here. Electrode potentials are measured at nearly equilibrium. This is what I was talking about. When we're talking about a galvanic cell, we're almost always at near equilibrium. But here, these voltages, we can add in whatever voltage we want. So we have the possibility of that over voltage, putting in a much higher voltage than is needed for the reaction to run. If two possible half reactions at the electrode, at one electrode, are within that range, that fraction of a volt higher, both half reactions will go. But it's hard to get an over voltage of more than a fraction of a volt. So the two half reactions have to be very close. And get back. This one here, you can see that this is not just a fraction of a volt. It's almost a full volt. So for over voltage to work, they have to be very close together. Okay, so the overall cell reaction then is the reduction of hydrogen at the cathode, and only this oxidation of water happens at the anode. So the overall reaction is that. So if we want this to take water and break it into hydrogen and oxygen, we could do it in pure water, but it requires a lot more effort, a higher voltage for that to occur. We put it in with sulfuric acid. That lowers the amount of work we have to do to separate this, because we're going to have to put energy in. Having an aqueous sulfuric acid solution makes it much less work. So even though we didn't seem like we did anything new here compared to the electrolysis of pure water, it actually is easier to do. Electrolysis of sodium chloride solutions. Sulfuric acid is fairly dangerous, and more expensive. So if you want to do the electrolysis of water using sodium chloride, that's going to be a cheaper option, but we have to be careful of over voltage. So let's look at the cathode reactions. Just like with sulfuric acid, there's two possibilities. We have what the water will do, and then what the, in this case, the cation, the sodium ion, is going to do. Sodium can be reduced to sodium metal, but look at this voltage that's required. It's gigantic. It's simply not going to happen because of that. But there's also another reason. If we make sodium metal, what does sodium metal react with very violently? With water. So if we were to produce this, say this voltage was a negative number, but smaller negative number than this, it still won't react, because as soon as you form it, it would instantly react back. So this is the only possibility here. At the anode, you have chlorine that can be oxidized to chlorine gas, and water can react. Now notice how close they are here. If we start putting a positive voltage across, we're going to meet up with this first. We're going to eat away at that negative number until we get to plus 1.23. Then it'll be 0 volts, and it'll be just ready to go. And then we go to 1.24, and then this reaction will occur. This one won't occur until we put in another tenth or so of a volt, but they're very close together. So under standard state conditions, water will be oxidized in favor of the chlorine. But over voltage is possible, so we got to be careful of that. So we can, with over voltage, we can produce chlorine gas, which is deadly. So if you're trying to do this, say in a classroom, you don't want to be producing this. The other thing, though, is that in dilute sodium chloride solutions, the oxidation potential of chlorine chloride is very negative. So water is reduced in preference to chlorine ion. So if you want to increase the sodium chloride concentration, the chloride concentration goes up. So this is the Nernst equation for the reaction. If you add up this reaction, and this one, you get this. But the important thing, you don't have to know this, the equation here. The important thing to note is that as the concentration of the sodium chloride goes up, this concentration goes up. So this term decreases, this term decreases, this whole thing decreases, and so it becomes more spontaneous. Because of that. So it's not, and so we can adjust the chlorine, make the chlorine gas form, make it the chlorine gas formation more likely if we use over voltage or we increase the concentration of the sodium chloride. So that's when you're doing this kind of reaction, you gotta be careful of over voltage and also of the concentration of the sodium chloride. Since sodium ion is left behind and OH minus is produced, if we evaporate off the solution, we are left with sodium hydroxide. So you can produce sodium hydroxide this way. Okay, and then the last couple of things here. Let me just check real fast. Yep. Okay, so electroplating of metals. Many metals are protected from corrosion by plating them with other metals that are more inert. Zinc is more inert, and zinc coatings can be used to protect steel. Not only will it protect the steel if it coats it, but even if it's scratched. So there is you get zinc is scratched away from the metal, it'll protect it just as the magnesium protects the pipe, this cathodic protection. So it doesn't even have to be covering it. As long as it's nearby, it'll protect the steel beneath it. So this application of zinc is known as electrogalvanizing. A coating of zinc is called galvanizing. So doing it this way is electrogalvanizing or zinc electroplating. And the reaction is very simple. At the surface of the metal that you're covering, which is going to act as the cathode, the zinc will react with 2 electrons in solution to form zinc solid right on the surface. And of course we have to apply, or we have to put energy into the system to get that to happen. Another thing we can do with electrolysis is metal purification. Copper, to be the more pure the copper is, the better it is as at electrical conductance. It has a higher, you want it to be as conductive as possible to electricity, so you need it to be very pure. So the way that they do this is they take slabs of impure copper. So they get the copper and they don't worry about making it particularly pure. They just get it into these slabs, and then they put this is in solution, copper 2 sulfate solution. And in between these can be dozens of these in a row. You have these slabs of impure copper, and then you have the pure copper in between. And in the process, what we do is we force the, let's see if I didn't leave myself a lot of room here, but the copper, the impure copper, is oxidized to copper 2 ion. And then at the, so these would be considered the anodes. The impure copper, I think I wrote it somewhere. The slabs of impure copper serve as anodes. That's where the oxidation takes place. And the sheets of pure copper serve as the cathodes. So at the anode, the copper metal turns into copper ion plus 2 electrons. That's the anode. And at the cathode, at the pure copper, the copper 2 ion reacts with electrons to produce pure copper metal. Very, very pure, because that's the only thing that's in solution now, is copper or copper ion. So it takes on the order of weeks or months to do this, but the impure copper is slowly eaten away, and the pure copper plates become coated with very, very pure copper. And this is why when we're doing reactions in the lab involving copper metal, we just use copper wire that's used by electricians, because that's all that copper, even though it's just something you find in the hardware store, is very extraordinarily pure. So we don't have to worry. We don't have to go to a chemical company and order some ultra pure copper. That's sitting on the shelves in hardware stores. Okay, so when the impure copper is eaten away, the less reactive metals like gold, elements that are in the impure copper, like gold, silver, and platinum, fall down to the bottom of the container in what's called anode mud. And there's lots of other crap in here. It's not just pure gold and silver and platinum, but mixed in there is silver, gold, and platinum. And that's one of the main sources of gold and silver and platinum for the United States, is in anode mud. So as we're purifying copper, we're also finding not a lot, it's low percentages of them, but that's where you can find gold, silver, and platinum.